In this video I will try to improve the sideband noise performance of this selective amplifier. Look at previous videos for how it works as amplifier and oscillator. I have been running it with the Ventzel 10 MHz ultra low noise oscillator at a particular setting on this attenuator and with this amplifier in front. The power level has been a little higher than I thought, 17.0 dBm. Now I set this signal generator to 10 MHz and plus 10 dBm, connect it to the spectrum analyzer, and I see 10.4. So there seems to be no problem with the calibration of the instruments. And I set it to minus 60 dBm now, and look at the spectrum analyzer, it says minus 59.2. So there is an uncertainty in the order of 1 dB, and that is how the instruments are specified. I have connected a low noise amplifier to the output of the selective amplifier, and that is connected to an SDR IP, and here you can see the spectrum from the SDR IP. At the center here you see the leakage from the Ventzel oscillator. It's about 100 Hz below 10.0, so I placed the BFO to read 10.0 for the Ventzel oscillator. And as you can see, it comes fairly close to the peak of the noise that comes from the selective amplifier. I think that is thermal noise from the crystals, or maybe noise from the FET amplifiers when they see a higher impedance. I have turned off the Ventzel oscillator, and as you can see, it disappears from the spectrum completely. I have connected this signal generator to the low noise amplifier, and then is this what I see, and I will calibrate the S meter to show minus 60 dBm, like this. Now I have a dummy load on the input, and the noise I see here is minus 163.7 dBm per Hertz. This is minus 180.7 dBc per Hertz with respect to the 17 dBm input signal. The noise is flat within something like plus minus 25 Hz or so. It means that with an offset of 10 Hz, the noise I see is minus 140 approximately when running the unit as an oscillator. That means as 10 Hz I need a signal to noise ratio of about 40 dB. 50 Hz below 10 MHz, the noise is minus 166.7 dBm per Hertz. 50 Hz above 10 MHz, I see from here to here, minus 167.9. On the average, plus and minus 50 Hz from the center, the level is minus 167.3, and that is 184.3 dB below a 17 dBm carrier on the input. The sideband noise level that I observed at 50 Hz is about minus 155. That means that the signal to noise ratio for a 17 dBm carrier is about 29 dB at 50 Hz offset. And it seems to me to get a better sideband noise level, I need to improve this signal-to-noise ratio because I cannot improve the Q. That would be far more efficient, but not possible without another type of crystals that would cost about 100 times more for each one. On the other hand, I wouldn't need as many, but on the third hand, then I couldn't get as good performance at wide separations as I can with this arrangement. Here I'm looking at an offset of 50 kilohertz on the flat noise floor. These things, they are spurs from the power supply of my computer, and they don't affect the noise floor here. The level I have here is minus 182.5, and forget about the calibration, it's just an arbitrary level at this time. I now disconnect the low noise amplifier and connect it to a dummy load, 50 ohms here. And you can see have it non-connected gives a very low noise, but with a 50 ohm source impedance, I see a level here of minus 188.5. So that's about 6 decibels higher. I changed the calibration of the S-meter to show 0 on the power within the bandwidth. The dummy load I'm using is the noise figure meter, the noise head of it, so I turn it on and I set it to 1 dB. It's not perfectly stable at these very low levels. And then I read what I see here. 2.7 means the noise figure is a little bit above 1 dB. So I try 1.2. And 2.8. So the noise figure is maybe 1.4 dB. Anyway, it is low, but the noise from the selective amplifier, far from the filter center, is still significantly above this level. Here. So I can reduce the gain and increase the power, hopefully then to get a better signal-to-noise ratio close to the carrier. I have increased this capacitor from 400 pF to 700. And this one I have decreased from 680 to 470. And of course retuned this to get the frequency back to the correct center at 10 megahertz. And I had to adjust this capacitor a little bit, make it slightly bigger to get the 50 ohm as desired on 10.0 megahertz. The gain is now about 4.5 dB lower, while the Q has gone down from 120,000 to 108,000. I think that is because on the gate of the FETs there is a small negative impedance that couples less to the crystals this way. I have connected this generator again to the input and calibrated Linrad to show minus 60 dBm. The noise floor I see now is minus 164.9 dBm per hertz at the center. I had minus 163.7 before doing the changes. So I have gained 1.2 dB in lower noise. And now I should be able to increase the power level of the input by 4 dB. So that's a 5 dB improvement in signal to noise ratio for the carrier, if everything is as I hope it should work. There could be problems from noise in the crystals, for example. Now the selective amplifier has been running for quite some time with 4 dB more input power to compensate for the loss of gain. And that gives the same approximately input level, 1 dB from AD saturation that I had before. I'm checking the carrier and I want to read it out to make sure that it is not changed too much. It has increased by nearly 0.1 dB, and I can understand that by looking here also. The average power spectrum is 0.1 dB above the correlation spectrum average. But this is just 0.1 dB and I neglect that. I'm looking now at an offset of 70 Hz. And I evaluate the noise here. 147.9 and with correlation advantage 9.1. That is a point here. It is not better than before, rather not quite as good. So it seems this was not an improvement, rather the other way. I will evaluate more carefully to see whether this holds. 70 Hz offset on the low side, 93000. The power spectrum is similar here, 148.6. On the upper side I had, it's a significant difference, 147.99. That was 148 and this is 148.5. And the correlation advantage here is 11.6. That gives me minus 160.2, which is here. The midpoint between here and here happens to be very close to the line which I draw between the midpoints from the measurement before I made this modification. So it seems noise has not improved. I will evaluate more carefully from this pixel editor. I have been running the Delta 44 in parallel to get better information at the very close range, and this has given this spectrum, and I have got the numbers here so I can read with the pixel editor. The correlation advantage at this point is 17, while the theoretical limit is 20. So it is marginally, I cannot quite trust the results here, but here it should be okay. And that is 30 Hz. One thing to observe is that the level of the 50 Hz sidebands, this one and that one, are very different. On the high frequency side it's much stronger. There is also a 60 Hz sideband, I don't know from where it comes. And I can see that the noise on the high side, here about this separation from the spur, is much higher than here at the same separation from the spur. So if the noise has an origin similar to the 50 Hz sideband, then it's natural that it's stronger on this side than on this side. And you can see also, of course, right above the 60 Hz spur we are here, but here we are on the bottom of the screen. So this will come clear from the table I'm going to make. The meaning of having different levels, this means that 50 Hz is AM as well as phase modulation. So the noise which is higher here, well, on the green curve, has to be a phase noise plus AM noise, which is correlated to some extent. To make sure that the unexpected result is not caused by my test system, I have made this filter to remove part of the noise on one side of the carrier. It looks like this. It's an offset of 270 Hz or so. The impedance is accurately 50 ohms in both directions, and the loss is 0.39 dB. So the arrangement is like this. The selective amplifier, 6 dB attenuation, a low-pass filter at 15 MHz, a stepped attenuator with 10 dB attenuation. And now that filter, and then into the hybrid that splits the signal into the two channels of the two-channel direct conversion receiver. What I see is totally unexpected to me. This filter does not remove noise, it adds noise. The crystal is pumped by the carrier here, and it gives noise on its own resonance frequency. And I can read what is the sideband noise level. It's minus 162, and the correlation advantage is 1.8, almost 0. I have moved the notch now to the other side of this 10 dB attenuator, so now it has 10 dB more power. And then this is what I have seen. There was an event here of high noise, a noise burst. Now, these crystals were not selected for not having these problems, so that's one thing. But if I clear the correlation and wait for a time when there is no noise burst, and I will try to find out what is the normal noise level. With the filter at the receiver input, the noise I see at 270 Hz, around that, was minus 154 dBc per Hertz. While describing the image in the video, I said minus 162. So that was a mistake. But what I have is minus 154 dBc per Hertz. The power into the notch filter is plus 16 dBm, that's 40 milliwatts. The loss in the filter is 0.39 dB, that's about 9%. So that means that about 3.6 milliwatts is lost in the crystals. 10 crystals are in the filter, so there is 0.36 milliwatts for each crystal, and that means that the drive level of the crystals is minus 4 dBm, so that's well within the specifications for the crystals. But they give this noise density on the resonance frequency. Now, with the filter operating at 10 times higher power, the noise is lower. There were strong noise bursts early but they have disappeared now. The level I see is minus 155.9 with 7.6 dB correlation advantage.